Okay guys, in this video we're going to talk about a few more concepts related to Lewis structures, formal charges, and the notion of resonance. So we'll start with the formal charge. Formal charge is a hypothetical charge on atoms which you can derive from a Lewis structure. And the reason we want to consider formal charges is because it's possible to generate different Lewis structures that satisfy the octet rule, but are still different from one another. And so the question is which of the Lewis structures is better amongst the ones that are possible? And so we can use these formal charges as a tool for distinguishing between different Lewis structures and choosing a better one. So first off, the formal charge, you can calculate a formal charge for every atom in a molecule. It's equal to the number of valence electrons that atom contributes minus 1/2 the number of bonding electrons minus any lone pair electrons that are present on that atom in the Lewis structure. So if you have a Lewis structure, you can calculate the formal charge on the atoms, and I'm going to show you some examples of that. Just note that the sum of all of the formal charges in a neutral molecule must add up to 0, or if you're dealing with a polyatomic ion, the sum of all the formal charges should add up to the ion charge. And so we are going to use these formal charges that we calculate to distinguish between different molecular structures, and we're going to try to pick amongst the different Lewis structures the best Lewis structure for a given molecule according to these rules. And so we want to choose the Lewis structure that has the lowest magnitude of formal charges. We want to choose Lewis structures that don't put like charges on adjacent atoms. For example, you wouldn't want to have 2 + 1 formal charges right next to each other. And then if you've got a Lewis structure involving an electronegative atom, you want to choose the Lewis structure that puts the negative charge on the more electronegative atom. It wouldn't make sense to have a positive formal charge on an electronegative atom. And so here's some examples for carbon dioxide. So if you'll recall from the previous video, this is actually the Lewis structure that we came up with for carbon dioxide. And then here are two alternate Lewis structures. One of them involves a different skeleton structure altogether. But if you count up the electron pairs, you'll find that each atom satisfies the octet rule. So how can you distinguish between these different structures? Well, you can do that by assigning the formal charges to the atoms. And so I'm going to go ahead and go through this with a specific, this example here. I'm going to go ahead and write it out, how to calculate the formal charge on each atom. So we'll start with the good Lewis structure, the one that we know is the correct answer. Okay, and we're going to calculate the formal charge on each atom. So for the formal charge on carbon, we're going to take the number of valence electrons in a carbon atom, which is 4, and we're going to subtract from that half the number of bonding electrons. So we've got 2, 4, 6, 8 bonding electrons. So we'll take away half of those. And then there are no lone pair electrons on carbon, and so there's nothing more to subtract from there. We get 0 for carbon. And the formal charge on the oxygens are going to be the same because they have the same electron dot structure around each oxygen atom. So each oxygen atom contributes 6 electrons. Okay, each oxygen atom has 2 4 bonding electrons. And then each oxygen atom also has 4 lone pair electrons. So we'll subtract all of these lone pair electrons from the formal charge on the oxygen. Okay? And we do that, we get 0. Okay? So in this structure, as it indicates here, the formal charge on each atom is 0. Now we'll do the next one, just to illustrate how you actually calculate these numbers. So drawing the Lewis structure here. Okay, now the 2 oxygen atoms are different, so we're going to have to do the formal charge for each of them. I'll start with the carbon again. Okay, so the formal charge on the carbon, we're going to start off with 4, the number of valence electrons, and then we're going to subtract half the bonding electrons. So we've got 2, 4, 6, 8, so we'll be subtracting that many. there are no lone pairs, and so we get 0 for carbon again. For this oxygen here on the left, I'll call it oxygen 1. We start with 6 minus 1/2, 2, 4, 6. Subtract off half the bonding electrons, and then subtract off the full number of lone pairs. Okay, so here we get 6 minus 3 minus 2 gives us a total of +1. And then for the other oxygen atom 2, we have 6 minus 1/2 times 2. There's 2 bonding electrons, and then there's 2, 4, 6. There are 6 lone pair electrons. And so we're going to get a charge of -1 on this case. So in this case, we wind up with +1, 0, and a -1. Now, compared to this Lewis structure, which has the formal charges all have 0 magnitude, this Lewis structure has some charges with magnitude of 1. And so according to the rules, this structure is better than that one because this one involves smaller magnitudes of charges. Okay, so using that rule A. This also places a +1 charge on oxygen, which is usually not a good idea. I'm not saying it's impossible, but it's usually not the best idea. And then for the other, for this Lewis structure that has a completely different skeleton structure, you wind up with a +2 charge on an oxygen and a -2 charge on the carbon. A, that has a large magnitude of charges, and B, it puts a +2 charge on oxygen, which, again, that's not a good idea. Oxygen is a very electronegative atom. It really shouldn't have a positive formal charge. So this structure is no good as well. Well, I think we're just going to do some more practice. And so on the next slide here, we're going to be looking at this interhalogen anion. Okay, so we get 7 valence electrons. We've got to first come up with the Lewis structure. So we get 7 valence electrons from the iodine, plus 4 times 7 from the chlorines, and there's one more coming from the fact that it's an anion. So we have 36 valence electrons to deal with. Iodine's going to go in the center. It's more electropositive than the chlorines. The chlorines are going to be satellites that go around like this. We'll write our skeleton structure like that, which takes into account 8 electrons. So we're going to have, let's see, that would be 28 electrons remaining that we need to fill in. Each of the chlorines we can assign 6 electrons. So we've just assigned, it looks like 20 electrons. And so, no, 24 electrons we just put on the board. And so we have 4 electrons remaining. Those are going to be distributed to the iodine. This is a hypervalent species. So this is the correct Lewis structure for this guy. Now what we want to do is assign the formal charges. So we'll start with iodine. Okay, the formal charge on the iodine, we start off with 7 valence electrons. Subtract off half of the bonding electrons. There's 2, 4, 6, 8. And then there are also 4 lone pair electrons. So that's 7 minus 4 gives us a -1 formal charge for the iodine. Then for each chlorine, we've got 7. Each chlorine has 2 bonding electrons, and each chlorine has 6 lone pairs. So we get a formal charge of 0 for each chlorine. Now the sum of the formal charges, so we've got 0 on all of the chlorines, and we've got a -1 charge, -1 formal charge on the iodine. The sum of all of the formal charges need to add up to the ion charge, which is -1 in this case. Okay, so these are the correct formal charges for this species. Let's do carbon monoxide. Carbon monoxide from a previous video we found has this Lewis structure. So this, let's do the formal charges on the carbon. I think we're going to get a surprise here. Formal charge for carbon, we've got 4 valence electrons minus 1/2 times the bonding number of bonding electrons, 2, 4, 6. And then we've got two electrons, 2 lone pair electrons. So we get 4 minus 3 minus 2 is going to give us a -1 formal charge on carbon. We do the same thing for oxygen. 6 minus 1/2 times 6 minus 2. We're going to get a +1 charge. Okay, so carbon monoxide is kind of breaking the rules here. We wind up with a positive formal charge on oxygen and a -1 formal charge on carbon. Nevertheless, this is the accepted Lewis structure for carbon monoxide. In the next one, part C is similar to part A, so I'm going to leave that one as an exercise for you guys. And I'm going to go ahead and leave part D as an exercise as well. Let's look at the next type of problems here. Here we're being asked to make decisions about different Lewis structures. So here we're looking at nitrous oxide. We have 2 different structures, and we're being asked to determine which of these Lewis structures is better. Okay, so let me copy them down real quick. And what we'll do is we'll evaluate the formal charges, and we'll try to figure out which set of formal charges makes more sense. So starting with this Lewis structure here, the nitrogens are in different environments, so I'm gonna calculate the formal charge for each nitrogen atom. So this will be nitrogen atom 1. We start off with 5 valence electrons, and then we subtract off 1/2 the number of bonding electrons. So there's 4, 2, 4, and then minus the 4 lone pair electrons. So we have 5 minus 2 minus 4. So we have a total of -1 on that nitrogen. For the second nitrogen atom, we start off with 5. This one has 2, 4, 6, 8 bonding electrons and no lone pairs. So we have 5 minus 4 gives us a +1 formal charge. And the formal charge on the oxygen, you may have guessed it, it's going to be 0. We start off with 6 minus 1/2, 2, 4, minus 4 for those guys, and that gives us 0. So we have a -1, a +1, and 0. Let's look at the other structure and see what its formal charges are. So here we've got the more symmetric structure. The 2 nitrogens now are electronically equivalent to one another, so I only need to calculate the formal charges on one of the nitrogens. So starting with 5 valence electrons for nitrogen, subtract off half of the bonding electrons, and then subtract off the lone pair electrons. So here we've got 5 minus 2 minus 4 gives us a -1. So each one of these is -1. And you probably already guessed the oxygen is going to be +2. Let's go ahead and check. Starting with 6 valence electrons on oxygen, -2, 4, 6, 8 bonding electrons. There are no lone pair electrons. 6 minus 4 is going to give us a +2. So this Lewis structure is putting a +2 charge on oxygen, which is more electronegative than the nitrogens. So really, between the 2 Lewis structures, this one is preferred. And indeed, this is the skeleton. When you look at nitrous oxide molecules, this is the structure that they have. They don't have this symmetric structure. Okay, and you can understand that through the formal charges. Well, we have a similar type of problem in part B. I'm going to go ahead and work that one for us. So we have 2 possibilities for nitrite ion. Okay, should the oxygen be the center atom, or should the nitrogen be the center atom? So let's take a look at these Lewis structures, and we will evaluate the formal charges to help us decide. Okay, we have a -1 charge. On the nitrogen, the formal charge on the nitrogen, we start off with 5 valence electrons and we subtract off the bonding electrons, 2, 4. Subtract off the lone pairs, there's another 4 that come off of there. So it's 5 minus 2 minus 4 gives us a -1 charge on that nitrogen. For the oxygen here, this will be oxygen 1. Start off with 6, 2, 4, 2, 4, 6, minus 6, minus half of 6 bonding electrons, minus 2 lone pairs. So 6 minus 3 minus 2 is going to give us a +1 charge on that guy. And then for this oxygen atom, we start off with 6 minus 1/2 times 2 minus 2, 4, 6. Okay, so we've got a charge of, let's see, this would be -1. Okay, so -1 plus 1 and -1 when oxygen is the center charge. Already it looks suspicious because it's putting a +1 charge on the central nitrogen. When we go to do the other structure, okay, we'll start off with this leftmost oxygen. So the formal charge on oxygen 1. Start off with 6 valence electrons, minus 1/2 times 4 for the bonding electrons, minus 4 for the lone pairs. So we've got 6 minus 2 minus 4, that gives us 0 for that oxygen atom. For the nitrogen, start off with 5, minus 1/2 times 6, minus 2 for the lone pair. So 5 minus 3 minus 2 gives us 0 for that one. And then for this last oxygen, you might guess that it's got to be a -1 formal charge. We'll show that. 6 minus 1/2 times 2 minus 6 valence electrons gives us a -1. The sum of the formal charges equals the ion charge. This set of formal charges is much better. This set of formal charges is much better than this set because the formal charge on oxygen is either 0 or -1. -1 is much better than a +1. And then, the overall magnitude of charges is lower, right? There's fewer atoms with a formal charge here than there are on this one. So this is the preferred structure for nitrite. And indeed, that's what's found experimentally. This structure is found, this one is not. Here we have a related concept, resonance. Resonance refers to situations where you have multiple Lewis structures that are equivalent to one another. Okay, nitrite is actually a good example. So these two Lewis structures, these could represent different nitrite ions. Okay, and the Lewis structures are different from one another. They are not the same, right? To give you an example of how you're different, if you were to look at the bond lengths and the bond strengths in nitrite, you would find that since the Lewis structure predicts that, or you would expect that since the Lewis structure here predicts that these two bonds are different, that perhaps the bond lengths in nitrogen and oxygen, like this bond length, would be different from that bond length, and that this bond strength would be different from that bond strength. You seem to see that the Lewis structure presents that the two nitrogen-oxygen bonds are not the same. However, experimentally, when one looks at the length of the nitrogen-oxygen bonds and the strength of the nitrogen-oxygen bonds in nitrite, they're both equivalent to one another. Okay, so we don't see that there are two different nitrogen-oxygen bonds in nitrate. Both of them are experimentally found to be the same. Okay, and so there's two ways that you can write this same Lewis structure, this way and that way. And the idea of resonance tells us that in nitrite, neither structure is actually what the case is. It's really a blending of the two. It's a hybrid of the two different resonance structures. So nitrite doesn't look like this and it doesn't look like this. It's really something in between the two. And that's what we call resonance. So all possible electronic dot structures that are equivalent to each other, or more or less equivalent to each other, um, are simultaneously occurring in nitrite. We call this delocalized bonding, meaning that this extra bonding pair isn't localized between these two atoms. In fact, it's delocalized over both bonds. Okay, so instead of there being a single bond and a double bond in nitrite, it's really something more like there's a 1.5 bond between between the nitrogen atom and each of the oxygen atoms. Okay, so the real case for nitrite is something in between these two pictures. Another example here is carbonate. Okay, so these are the best Lewis structures for carbonate, and you'll notice that they're all equivalent. The difference is just which oxygen atom has the double bond with carbon. You know, if you look at just one Lewis structure on its own, it indicates that there are two single bonds and one double bond in carbonate. But really, when you look at carbonate experimentally, what you see is that all three carbon-oxygen bonds are identical to one another. Okay, and that means that what we have here in carbonate is another example of delocalized bonding. These are called the resonance structures for carbonate. And so the actual picture for carbonate is that all three states are occurring at the same time. That is, you don't have two single bonds and one double bond in carbonate. Really, you have something in between single and double bonds in carbonate for all of the carbon-oxygen bonds. And when we express the resonance structures, we use these double-sided arrows to connect the resonance structures together. Now, this doesn't mean that carbonate is flipping back and forth between these two structures. What it means is that all three structures are equivalent to one another. Carbonate is some blending of the three, the average of all of the Lewis structures is a better way to think about it. Okay, so that's resonance. Here we're being asked to look at the resonance structures for a couple of different cases. We'll look at nitrate first. So nitrate has nitrogen in the center, and then there are three oxygens that form the satellites. And let's get the Lewis structure first. So we start off with 5 valence electrons from the nitrogen, plus 3 times 6 for the oxygens, and then there's 1 extra electron here. So we've got 18, 19, we're going to have 24 electrons. We have the 3 bonds here in the skeleton structure, so we're going to subtract off 6 electrons there. So that's going to give us 18 electrons to work with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We filled in all of the electrons. We want to make a double bond between one of the oxygens and the nitrogen. And so to make an octet for the nitrogen. And so I'm going to draw that here. However, we could have done it in a different way. We could have also, instead of putting the double bond here, we could have put it here. Or, instead of putting it down here, we could have put it over here. And so there's a third resonance structure. I guess it would help if you could see those. Okay, so just to backtrack a little bit, here I'm counting up the electrons. This is my skeleton structure. I assigned the 18 electrons. This is what I have. I'm missing an octet on nitrogen, and so I make a double bond here, and that gives me this Lewis structure here. But I could have also have made a double bond between the nitrogen and this oxygen atom here. The third possibility is that I could make the double bond between this nitrogen and that oxygen. Like so. And so this is the third resonance structure. So nitrate isn't one of these structures. It's the average of all three. Okay, so you don't have one double bond and 2 single bonds. What you really have is all 3 nitrogen-oxygen bonds are in between a single and a double bond. We call these the resonance structures. Benzene is another famous example of resonance. from organic chemistry, C6H6. So benzene is a ring of carbon atoms. They form a hexagon. Each carbon is bonded to a hydrogen, like so. And then to make octets, you have these these double bonds that are present. So notice that there's 3 single bonds and 3 double bonds. Okay, but if you look at experimental evidence, how many, what are the different bonds? What you find is that all of the carbon-carbon bonds in benzene are equivalent to one another. So really what we have is delocalized bonding. That is, these extra electrons here, they're spread out over the entire ring, giving us this second resonance structure here. And so here I'll put the double bond there, and a double bond there. We still have the single bonds to the hydrogens. So benzene does not consist of 3 single bonds and 3 double bonds. Really, all of the carbon-carbon bonds are in between a single bond and a double bond. I will leave the ozone for you. Just know that if you try the ozone problem, it's not a triangle. It's a quasi-linear molecule. It's not actually a linear molecule, but the atoms are connected in this fashion. They don't form a triangle. Okay, so this is the structure for ozone. I'll let you try this one. Try to generate the resonance structures for ozone. For this last topic, I wanted to talk about metallic bonding. So we've talked about ionic bonding, we've talked about covalent bonding and Lewis structures. Another type of bonding that we see in chemistry is metallic bonding. And so here we're talking about a metal. We'll take sodium as an example. Sodium has 1 valence electrons. What the solid sodium looks like at the atomic level, it looks like a crystalline lattice of sodium plus cations. And then those valence electrons are completely delocalized across the crystal. That is, that last s electron in the sodium, it's not bound to any particular atom. It's shared essentially with all of the atoms. And so we say that it's a crystalline lattice of ion cores, cation cores, surrounded by a sea of mobile valence electrons. And it's the fact that the electrons are not attached, the valence electrons are not attached to any particular sodium atom, is what makes metals so conductive for heat and electricity. It's also what gives it its malleability and ductile properties, so that you can hit a metal with a hammer and it deforms instead of breaking apart like a crystal, like an ionic compound. Anyway, so that's metallic bonding. It's sort of the ultimate of resonance, right? Where the electrons in a metal are completely delocalized and totally mobile throughout the entire crystalline structure. Well, I'm going to go ahead and stop this video here, and in the next one we'll talk about the relative strengths of ionic and covalent bonds.